Hi everyone. I want to talk today a bit about some custom language extensions to C++ that the company I work for, Embarcadero, has been doing for the past, I say 20 years. I think it's actually 19 years, but close enough, a couple of decades. So my name's David Millington. I work as the C++ product manager for Embarcadero. Email is up there in case you want to contact me. And we make C++ Builder. Now, we extend C++ for a couple of reasons. C++ has always had experiments and libraries and that kind of research kind of projects. And I want to focus today on some things that have been historically and still are today hard to do in C++. The particular one of interest to us are user interfaces with delegated events and controls with properties and that kind of thing. This is the kind of problem that Qt solves with mock. And delegated events or some kind of function handling can be handled a couple of different ways. Obviously, there's func and bind. We have something called a closure. I also want to talk about runtime reflection, or RTTI, which I think is something of interest to a lot of people. You always see questions about RTTI in C++ all the time. In fact, the talk just before this one was about an RTTI system. You Google, you keep on seeing systems that people have made. It's a really important thing that we don't have. So we have our own extensions to provide this. And one interesting thing, the use of metaclasses to provide virtual construction. So I'm going to look. I have 1 hour to talk, so I'm going to go very briefly through 4 separate language extensions. The first is properties, then RTTI, or runtime reflection. An object-oriented method pointer, something that today we would probably do a little differently, but is still interesting because of its approach to types, and metaclasses and virtual construction. So, as I said, I work on C++ Builder, and the product has a history of about 20 years or so. We have a booth today, and a whole bunch of people have come up and said, hey, I either use or used to use C++ Builder. But I do get the impression that it's not especially well known in the C++ community. There are many more people who don't know about it. And I think that is important because we are seeing language proposals in C++ to address a whole bunch of areas, such as RTTI, such as metaclasses. And I think awareness of any pre-existing implementation is worthwhile. You can always, when you know about something that exists and works, you can then improve it. And that is the aim of the talk today. I'm going to be talking about these extensions, and I'll talk about what's good and what works, and I'll also talk about what doesn't work, what we should improve, which could just be of interest to you, or if this kind of thing ever goes into C++ itself, I think it's the kind of information that would be useful. So, yes, what can we learn, what works, what should be done differently? So many of you might remember Borland. Borland was a famous developer tools company, Turbo C, Turbo C++, Delphi, and other tools. And Borland spun off its developer tools into Embarcadero, which is the company that I work for. So we still make Delphi, and we make C++ Builder, which is a sister product to Delphi for C++. These days it focuses heavily on sort of cross-platform libraries and, as I mentioned, UE frameworks. So I want to take you back in history to about 1999. This was the days of Windows 98, perhaps Windows 98 second edition, if you were lucky. And we're all really excited about having gradient title bars, and Winamp ruled the world. But for C++, we already had C++ 98, which was key for C++. We already had the STL. Now, it wasn't modern C++, as in C++ 11, but the foundations of the language that we used and an awful lot of code bases still use were in place. But there were at the time, and there still are, problems that C++ doesn't solve. And so Borland at the time wanted to create a C++ product, but it had these same problems. And so they decided to solve them through language extensions which we have maintained or tweaked or improved or added to or something over the years since. The main purpose there was cross-language integration, mainly with Delphi, and that's compile time. The two languages share a common ABI, and you can have classes in C++ that inherit from classes in Delphi and that kind of thing. And especially UE design tools. So our tools have always focused a lot on visual design, and these days we have a cross-platform framework that's Windows and iOS and Android and Mac and that kind of thing. And we tried to hook this up to C++ code well. And this, of course, is exactly one of the problems I just mentioned. It's difficult to do this. And it's been solved with C++ in a number of different ways. There you go, screenshot. Normal IDE, UE design tool, that's a mobile app. But you can see things like properties, for example, which you'd all be familiar with from other tools working in C++. So, yeah, I feel these extensions are interesting but largely unknown. So I'm going to talk about those 4 extensions, all of them very briefly, very lightly, and if I can, with time for questions at the end. The first are properties. So property is an abstraction of the concept of a field. So we have a member field of a class, and it's a value, you can read to it or write it, all that kind of thing. A property is an abstraction of that concept. For example, you might have accesses of various types, or you might want behavior that occurs, or you might want a value that's calculated on the fly rather than actually being a static value or something like that. So today, to achieve these kind of things, it's quite common just to have setter and getter methods, which when you think about it means that you have different names for the same thing depending on how you access it. Get something, set something, maybe read or write or something like that, but the point is you have different methods and different ways to access one thing, which when you think about it is a little crazy. Why do you have different names for one particular item? With a property, you have a single name, and the name doesn't change depending on how you access it. Now, there's several compilers that have implemented custom properties, and properties, again, is something that you see people pop up, especially when they're new to C++, and they ask, I haven't found this feature, how do I do it? So Microsoft, for example, has a custom property, and we do as well. And of course, any read-write abstraction can be extended to other read-write methods, such as indexed access or delegating the read and write or something like that. So we have an underscore property keyword. So the syntax you can see on screen. Let's assume that you have a class with, let's say, a member variable of some sort, which is a float, and a setter method. You want something to happen when you set a value. That could be anything. You might want to trigger something. You might just want to validate it, anything like that. Now, the key thing to get here is that you can declare a property, you give it a type, you give it a name, and you can give it optional read and write accesses. And they can be backed either directly by a field, so you can see the read one here is specified, so just get the value directly from the field, or by a method. So both reading and writing could be methods or could be fields directly. And that means that you can have behavior on reading or writing. Then we extend that with indexes. So I have an example there of 2 indexes, a row and a column. And in this particular example, I just have a read method. There would be a cell value method defined perhaps in the private part of the class or protected section of the class, taking a row and a column parameter. So the compiler simply maps this fairly easily. If you have code that mentions cells, then it will simply map that, in this case when reading, to invoke the cell value method, passing row and column as the 2 parameters to it. So that's a fairly standard property, read or write, index property, and we also have another extension which is to specify what the default value of the property is, and this is used when streaming, especially for when you have visual controls, because visual control normally has a number of default values. It's let's say the caption of a button, every time you place a new button on your form, it'll just say, I am button or something like that. And that would be the default value. Now, that's not used for reading or writing. It's simply used when streaming as a way of comparing, have I got the default or not? Do I need to actually stream this or not? And we'll get on to streaming and RTTI later. So I want to give a quick sort of overview of what's good or bad about this kind of thing. So with the property code sample up here, I chose the index one because I think it's a good example of a moderately complex but understandable property statement. In this case, reading and writing, both back-by methods, but as I said, you can mix and match. You can't really pass a reference to a property. When you think the compiler sort of changes this perhaps to either a direct field or a method call under the hood, and of course you don't know which. As the user of an API that's defined in terms of properties, you don't know how it's actually implemented. That's one of the values in that it's an abstraction, but you can't rely on any particular implementation. So you can't really pass a reference to it. It makes it difficult if you want to invoke read behavior through a reference to a method or forward or anything like that. So you can invoke read and write via RTTI, which I'll get to, so you can create some kind of binding to it. But again, that's only at runtime. But that said, the wrapper is very convenient. Properties are the kind of thing that people constantly ask about. They ask you, where is this feature? How do I do this? And the answer usually, if you read on Stack Overflow or something, someone's popped up and they're new to C++ and they're like, where is this? And the answer is, well, it doesn't exist. But it's asked about for a reason. It's convenient for a reason. This kind of abstraction is useful. And of course, when it comes to something like a visual control where you actually want to configure something visually, you want to set properties in some kind of editor on screen, not in code, or you want to stream, then this particular abstraction is really convenient. In terms of those issues about forwarding or sort of not runtime but a compile time data to provide better binding or something like that, I think those are issues that could probably be solved as well, especially given the direction the language is going with how it handles functions in general. We have std_func and std_bind that sort of handle all sorts of things. Conceptually, perhaps something similar could be done with a property, which would be an interesting thing to explore. This just goes into a few more details. A couple of things that are interesting are that you can redefine a property in our implementation. And of course, you can override accessor methods, and I think that's useful because you can then get virtual behavior. But as I said, this is particularly convenient. One other thing that's useful for events. So code that needs to be invoked when you have a particular event. You need some kind of binding that you can define. And we do this through an object-oriented method type. And given it's a type, then you can just have a property, a field abstraction of that type. And that's very, very useful as well. Okay, super brief overview of something that exists, a quarter of the way through in time and a quarter of the way through in features. So I want to talk about runtime reflection and RTTI. Again, this is something that you see asked about a lot. I think even far more than properties. Properties are asked about by people who are new to C++. RTTI is investigated by people who've used C++ for a long time. You constantly see libraries popping up that provide some kind of RTTI access or some kind of compile time access to fields or something like that. And there are proposals appearing about this kind of thing. Now, I want to differentiate as well between, I suppose, what you would call compile time reflection versus runtime, where compile time, something can be evaluated by the compiler at the time that you actually compile the code is very C++. runtime behavior can be more flexible, and this is a runtime RTTI implementation. In that sense, this version is not very C++ in that it's not something the compiler sort of evaluates and solves at compile time, although I do think the added flexibility is very, very useful. And I'll get into some of that in the next couple of slides. But here's the goal that we have had with our RTTI. For any class, a class type or a class instance, you should be able to query or iterate over the methods and the properties and the fields. So you should be able to say, give me a list of all the methods that you have, and then find information about them. Or you should say, do you have a method by a particular name, and if so, give me some kind of accessor to it. You should be able to invoke methods, or you should be able to read and write properties, and you can use those to implement some kind of binding between a property by name and value. So this is particularly useful for a few things. It's really useful for streaming of either, well, perhaps known at runtime types, and this is why we've gone for runtime RTTI, not compile time. So imagine, for example, that you have some kind of base class and you're going to be dealing with that, and you don't really need to worry about what the descendants are because, magic of polymorphism, you can just always write your code as though it's the base class. But the descendant class will have its own properties of some sort that will affect its own behavior. Now, compile time, you don't necessarily know what that is. Things can appear and be registered or instantiated at runtime based on different conditions. So if you want to stream based on that, or if you want to create something based on that, then this comes in particularly, is particularly useful for that. Or you can extend that to any sort of map between a structure and data storage or representation. The key here is that what you're streaming, and in fact the kind of object that you might want to stream to or from, the class itself, the solid type, is not always necessarily known at runtime. At compile time. Obviously you have all your types at some point, but you don't know which one you're going to be working with. So our RTTI works with the help of the compiler. It emits data about various types, and that data is built into the binary, the exe or the DLL. And you can then read that through RTL methods that will give you answers about it. Now, for us, it's for a special subset of classes, so it's not for all C++ classes. It's for a subset that come from a particular class, which we call TObject. So we have a rooted type system starting at that particular class. And one of the reasons for that is that these particular classes, TObject and so forth, have a whole bunch of other behavior as well. Including metaclasses, which I'll get onto in a few minutes. But basically, you can ask for the name of a class and the type of a class, which will return the metaclass, which I'll get onto in a few minutes. And you can get a pointer to the type info for any class. And the type info, and I've omitted some parts of this, contains a bunch of information about what it is, whether it's a class, it might be an enumeration or something like that. And its name, and then a whole bunch of data about it that is what lets you implement things such as iterating over methods or converting between name and something else. Now that's the one of interest. So depending on the kind of whatever it is that this type data is pointing to and has that kind field, we have a union that just holds a whole bunch of information. So, if it's a method, then, where is it and what's its name? Or if it's a field, how to get the address. And if it's a property, does it have a read accessor? Is it backed by a field? Is it backed by a method? That kind of thing. You can use this to map between enum values and names and all that kind of thing. And it's used to read and write fields, to find methods, read and write properties, that kind of thing. You can also look up by name. You can use an address and ask what you have an address of, that sort of functionality. There's a whole heap of other information. As I said, there's a very high-level overview, a whole heap of other information for each one of these particular things that you can get type data about. So I have one thing up on screen here. For example, for a method, is it a constructor or a destructor, or does it have a return type, and if so, what is it, and what are its parameters, and does it have a calling convention? What is the calling convention? Everything that you need to know about any part of a type. So this is used originally and still mainly today for streaming UE controls to and from the designer and creating them at runtime. So I have a sort of mock-up on screen. Let's assume you have a window that you're designing and has a Hello World button on it. Now we have a visual designer, of course, the way all tools do today, but this is actually stored internally as in text format, human editable text format, which is streamed and is streamed using this RTTI system. So this window, which contains just a button, has, obviously I've trimmed things out, but it looks like the column that you can see here, where you say, okay, I have an object called myForm over class tForm, and it has indented a button, which is tMyButton, which has properties. Caption equals hello world. OnClick, which is an event, equals button click. That's referring to a method. And these roughly map to these classes you can see here. Again, super chopped down just to fit on the slide. But properties that I mentioned earlier, here is a string property, which called caption, which you can see being streamed over there, or an onClick method. The method has a particular type, and you can see that being streamed over there. So how does this work? This streamed information is again built into the binary, and then these objects are created dynamically through virtual construction. And it will simply query what type are you and what do I expect to find based on the streamed text, and then instantiate all the fields. If you have a button, that's simply a field in a class. It'll create an instance of that, and again set its properties all through the RTTI reflection of what it expects to find. So that sounds really useful. It's probably a paradigm you're familiar with, achieved in other ways through other types of bindings, but we're missing something. Suppose you read a text file of the sort that I just showed on screen. How do you know how to create a particular type? So the window there had a button, which is a T button. How does it know how to create that? And again, something that's important to stress is that these aren't always known at compile time. We actually have something which we call packages, which are a little like assemblies that can contain classes, and you can load those and you'll get a whole bunch of different types. And so you can have something that you have a name of a particular type and you need to create it. So how do you do that? Or, for example, you'll have data for some kind of base class, but the one you actually want to create is a descendant class. How do you actually create the descendant that you particularly want? So we do this at runtime. And the connection between this concept and the way it's, the missing link here that we haven't quite got to is the use of metaclasses. And metaclass allows you to instantiate classes via the metaclass type of the base type that you know about, which you can use to instantiate some kind of unknown descendant inherited type. So before I get onto that, I want to, again, just sort of give this quick examination. What's good about it? What can we improve? That kind of thing. So for us, as I said, this is only for special classes, starting at a particular type of object called tObject, where all descendants of tObject can pick up this behavior. But of course, it would be better if you could do that for anything. Any class, any C++ class, any struct. Now, it was originally designed for another language, Delphi, and it was mapped to C++. And that has a couple of side effects. One of them is that we occasionally get two different type names. So you say, what type is this? Now, in Delphi, in Unicode world, it has a car, and if you're C++, there might be a WCAR-T. It doesn't really get in the way, it's just sort of an interesting quirk. And the way this tends to work is, I think, probably the least sort of traditional C++-like thing that we're going to see today, mostly because it was mapped from another language to C++. So iteration, for example, isn't particularly C++-like. You just get an array and a length, and you have to write a for loop. We don't have good support for C++ constructs, such as you might want to write a range-based for loop to iterate over something. Currently, you can't do that. No reason you couldn't, but currently you can't. And it's also quite basic. So for properties, for example, we have a special visibility specifier called published. And only published properties are the ones that are actually accessible. Now, we've already solved a whole bunch of these things and extended RTTI much further than what I showed you today. So we have a second revision of RTTI. And it gives full RTTI about everything in a class. So properties, for example, even private ones. Method invocation is much better supported. You can intercept virtual methods. You can do all sorts of things like that. Now, for us, that is not yet exposed to C++. And we do plan to do that, but we haven't implemented that yet. But I think this is useful because it shows, first of all, that you have a first cut and then you need to revise this, especially based on something that should be a bit more C++-ish, and that we plan to do that in future. If we designed it completely from scratch, which we aren't because the original beginning of this was 19 years ago, but if we were, would we do it completely differently? Would we try to hook into C++'s own quite basic RTTI? Would we aim to have it for any class rather than just ones from that descend from a particular class? Probably yes to both. And I think especially for method invocation, especially in the past couple of years, we would implement that differently. We would either make use of func and bind or make use of some very, very similar mechanism. But in practice, it works really nicely. It's very powerful and very flexible. And this is used by lots of people every day in C++. And it works really well. I think really that's one of the important points, because when you get down to it, the practicality of something is perhaps a bit more important. Does it work? Does it work well? Yes, that's good. So, I want to get on to the third one. I'm now halfway through time and halfway through the only four. There are a lot more, but the four sort of extensions that I want to talk about today. I'm just going to fill up my glass. So, there's a really nice proposal for metaclasses by Herb Sutter, I think, which I've read, although I have to admit I need to absorb it better than I have done. Now, in our terms, in Embarcadero's terms, in C++ Builder's terms, I think we would phrase that particular proposal as something else, as an interface, or as some kind of extended interface. So stuff I'm not even going to show today are an interface keyword or COM-compatible bindings and interfaces. But that said, that metaclass proposal, from my understanding of it, is fantastic. It's awesome. I'd love to see it. But today I want to talk about a slightly different take on metaclasses, which is inspired more by the Smalltalk style of object orientation. C++'s object orientation concepts don't necessarily come from Smalltalk. When you read about the original inspirations for it, languages like Simula are cited, but not Smalltalk. But we've always sort of approached things just in the company with much more sort of runtime, dynamic kind of approach than than might be normal for C++. And so we have something here that's inspired a bit more by a Smalltalk-style metaclass. So we have here a class of class. If you were to represent a few classes, what is their common behavior? What is the meta information about them? And this is closely tied to RTTI, and it specifically is also used for virtual construction. So a couple of slides ago, I had a sentence up on screen which said, and uses metaclasses to instantiate classes via the metaclass type of their ancestor. And this is the sentence that I'm going to be unpacking in the next couple of slides. Before that, though, I want to quote here, why don't we have virtual constructors? This is from Bjarne Stroustrup's FAQ. So to quote from that, a virtual call is a mechanism to get work done given partial information. In particular, virtual allows you to call a function knowing only an interface and not the exact type of the object. To create an object, you need complete information. In particular, you need to know the exact type of what you want to create. Consequently, a call to a constructor cannot be virtual. So the key bit there is to create an object, you need complete information. You need to know the exact type of what you want to create. And that is where a metaclass comes in, because the metaclass is what provides that information. So let's assume you have a base class and a couple of descendants, descendant A and descendant B, and you have a virtual constructor. Now, the metaclass is the class of your base class. And so the classes of your descendant classes are polymorphically compatible with the metaclass of the base class. So that gives you something that in pseudocode would look like a base metaclass pointer equals underscore class ID. This is one of our extension keywords of the descendant. Now, this code here, class ID of the descendant B, will give you the metaclass for the descendant B's, for the descendant B type. But of course, because metaclasses themselves are just classes, it's compatible. It's just a polymorphically different descendant. Then, though, you can call the constructor, and although you only have the metaclass that you believe you're interacting with representing the base class, the actual instantiated type will be of the descendant. The metaclass contains other information as well. It gives you the name, it gives you the instance size, you can query inheritance and all that kind of thing as well. But I think the main thing here is the use of metaclasses to implement virtual construction. So, obviously you might have something far more normal code. You have a pointer to a base class and you create a new descendant. But the key thing here is what if you don't know which descendant you will need to create. And so you can have something that will return a type, and then you can create based on that type. Now for us, we implement this with classes registering themselves. So there's a central database of class types. And so you can look up by the name of a class, and you can get the RTTI of a class, and you can get the class type, the metaclass. And then, of course, through that, you can invoke a virtual constructor, and you can get some kind of descendant that's chosen purely at runtime. Just some kind of side note. There's a thought experiment here, or something that people have asked me about in the past discussing this. C++ classes, when you normally create them, when you normally invoke a constructor, aren't aware of their full type during construction. This is what leads to the rule, don't call a virtual method in your constructor. And the reason for that is that the type isn't fully defined. But a thought instruction is that the virtual construction implies something different. And now we actually don't implement that. We follow the C++ construction rules, but it is an interesting side note of something that could be interesting. So, examining these, they're a really elegant concept. They're very closely tied to RTTI, and they're very useful for virtual construction. Now, despite everything I just said, they're actually not fully implemented. So the meta class is in our implementation of both the base and descendant are actually internally represented by the same thing. So we have just enough to query things like an instance size or a name, or to invoke a virtual constructor. And this would be really good to extend. And I think we could also make it a little more C++-ish, such as getting some kind of function-like object to represent the constructor call. Currently, when you want to call the constructor, it's a little bit ugly. And again, it's only for T-object descended classes, not all C++ classes. Alrighty. Finally, I want to look at the fourth language extension, and this is one that up front I want to tell you we would do completely differently today if we did it from scratch. So the purpose of this one is specifically to handle events. So you have a control with an event such as an onClick, and you want to invoke a method when the control is clicked, but you want to do that through the property binding, which you want to stream. So you might have different unrelated classes, but you have methods with the same signature. Here I have class A and class B. They don't have some kind of common ancestor, both with a foo method. They both introduce it themselves. But the signature is the same. So how do you invoke that? Well, in the old days, you would have C-style method pointers. And so this was written as an extension to a C-style method pointer to say this is actually an object-oriented method pointer. And did that by introducing a keyword called closure. Now the syntax is C-like, not C++-like. And I think the name of the implementation probably made more sense back in 1999 than it would today in 2018. But to show you how this works, the method on screen, void class foo taking an int, becomes the typedef that you can see on screen, typedef void. The keyword __ closure, which is what says, hey, I'm not just a normal C method pointer, but I'm a pointer to an object-oriented method. I have a this param. And then the rest is fairly straightforward. The syntax, though, is much nicer at the time of use, because once you have a type like that, you can just define a variable of a particular type that represents a function, and you can assign it just by getting the address of an instance's method. So there, tMyMethod equals address of myObject.foo will capture both the address of the method itself and the object instance. And so these things are stored internally as a pair of pointers to the object instance and a method, and invoked just with function syntax. You can just call them with the parameters. The this that is captured is implicit, and it's a very simple type. And so that's why they're used for properties and for events. Now this can be quite useful because it's type agnostic. It binds effectively purely based on the signature, not on a particular class type. But I think the naming could be better. I mean, a closure, especially today, does not mean just capturing the instance pointer. It means capturing the environment. My guess as to why it was called closure back then is because it was capturing some of the environment, which is the instance, but that's it. So even today, even if we were to go the route of some kind of extension of a C-style function pointer, which I don't think is what we would do, definitely have a different name. But as I said, the syntax is C-like to define it, not C++-like. And it's not compatible, because of that, it's not compatible with all functions. So you can't assign a lambda to an event, for example. So today, if we were to do this, and in fact we may extend or change our implementation to do this, we would use something far closer to the way C++ more generically handles function objects in general. So that you could assign a lambda, for example, to an event handler. Alrighty. Now I'm trying to go through all these very quickly, mainly because I wanted to not go over time, but I also wanted to leave some time for questions at the end. So we saw a very brief overview of 4 extensions. We saw properties, something that other compilers do as well, but we abstract a little further, I think, through backing through fields and methods, as well as indexes, and of course they are exposed via RTTI, so you can get an almost complete examination, iteration, querying of types, not just of classes, but of everything about a particular class, such as an enumeration, including the enum type. You can go between the value of an enum to its name very easily, or you can query a method, and you can say, what is this? What does it return? What are its parameters? What type are they? That kind of thing. And interesting, although something we probably do differently today, although it works very well, but something we would probably implement or design differently today, an object-oriented method pointer. There's a bit of history I didn't mention there, but if you sort of take yourself back in time, how to implement object-oriented method pointers was something that used to be asked about a lot in C++. It's been resolved now with the extensions to the language, but it used to be something that there was no good way to do. People would come up with interesting templates, but we had a language extension instead. And of course, metaclasses. Interesting implementation, very powerful, I think, because of the virtual constructor call, something that we could flesh out a little more. We have enough there to achieve our particular goals, but I think it would be really interesting to flesh that out to provide a much stronger separate class type for each class of class. So again, I mentioned with this, I really wanted to provide both an overview and sort of an examination of what's good, what's not so good, the changes that we might make if we did it today, changes that we might make in future, because of course we have this compiler, we use Clang, by the way, and we extend it with these keywords. The nice thing about being a compiler vendor is that you can do that, and you can also change the implementation if you want. And so things like this, where we have something and we look at it and say, yeah, that works well, but perhaps we should make it a bit more C++-ish. Well, that's the kind of thing we can do, and we are looking at doing. Also, I think it's just interesting. It's interesting to see what's out there, something that you might not be so familiar with, especially RTTI, I think, but other things as well. Implementations out there, implementations people have been relying on and using for a couple of decades that are perhaps not so well known. I know that some of the proposals that I've seen even go up to the Standards Committee are completely unaware of some kind of prior existing implementation that it could be useful to be aware of, to build upon. And even if you don't want to build upon it, I think it's really useful to know it exists, to be able to say, okay, it did it this way, some things are good, some things are bad, let's learn from that. Also, I think it's particularly interesting because it's a glimpse of a slightly different C++, of a slightly more runtime-focused C++, and a slightly different influence in the direction of the language. And so we use all of these for our cross-platform frameworks, especially for the UE libraries. We have cross-platform UIs run on Windows and iOS and Android, macOS, and all of them have this, make use of all of these techniques. The interesting thing there is that you don't actually see any of this when you write C++ code, because all of this happens under the hood. When you have a window and it is created and it will stream itself and it will create its own fields, that's code that you never actually have to see, you never have to write. All you have is the definition that you visually design, and which is streamed to that text. But all the handling of that is never actually explicitly code that you have to write or see. So all of this happens under the hood. It's something that you don't actually ever look at. So, that said, I know this was really brief, really high level, not much code on the screen, but I hope it was interesting. Now I'll open it to questions. Thank you. I certainly hope there are some questions. I think in your place I would have a lot of questions.
I
Yes.
A simple question. You've repeatedly used the word stream when you refer to windows displaying themselves. I can't connect that with my understanding of what streaming normally means. So maybe you could explain what you mean by streaming.
So the question is, what did I mean by streaming when I was referring to forms and visual controls? Perhaps I used the wrong word. Perhaps I was misleading. But what I mean there is you have a form with a bunch of other controls on it, buttons, child fields, basically. And how do you go from that to a textual representation? That's streaming to text, to take the whole object hierarchy with the types and with the properties, turn that into sufficient textual, human-readable format of some sort that you can then reverse that, and then from that textual format go back and recreate the entire class hierarchy, recreate or fill in the values of all the properties, hook up the methods, that kind of thing. That's what streaming is referring to. Yes, there's a question at the back.
You said all this is implemented now in Clang. Is it under some flags or can be used in other projects without C++ Builder? So
the question is, I said that this is implemented in Clang. Is it usable only in C++ Builder, or is it implemented, accessible by other projects? So it's only C++ Builder. So we extend Clang with these language extensions ourselves, but those extensions are currently in-house, in our own repo. So you can use our compilers, of course, but we haven't published the code for these extensions. I know that quite a long time ago, I think circa 2002 or something like that, the whole sort of property method event paradigm and the property system that we saw was actually proposed to the standards committee, and at the time that kind of thing wasn't really something they were looking for. I think today we're probably far more aware of the need for something like that. So it'd be interesting to go ahead and perhaps work with other people and create something that is accessible for a lot of compilers rather than just our own Clang branch. But meanwhile, yeah, it's our Clang that this is implemented in. Are there other questions?
Well, I have another question.
For sure.
Didn't want to be greedy. No, just when you talk about the object-oriented method pointers, you said it's about having pointers to unrelated methods that happen to have the same signature kind of thing in two different classes. And the obvious question there is, why not have a common base class for them, particularly when you've got multiple inheritance in C++ anyway? Why is it so objectionable just to give those two classes a common base?
So the question is, with events and with methods, I mentioned that the closure type, the object-oriented method type, worked based on the signature, not on the type. And the question is, why isn't there some common ancestor type there? I think originally it was to do with the concept of, and I'm speculating here, but I think originally it was to do with the concept of event delegation, and didn't want to tie too closely to some kind of required object hierarchy. When you have something like a button click event, that click event can be implemented by any other class. You might have a click method on the form, or you might have it on some other layer completely. Today you would probably have some kind of MVC or MVVC or something, something that takes that. But I think the designers originally didn't want to require some kind of particular type. I think they just wanted to say you can delegate to anything. Now you could probably enforce that a bit more strictly by having some kind of ancestor type. But if you had some class that was used for this delegation, it might inherit from 100 different types just to say, okay, I can handle this kind of event, which may not be a particularly clean way to do it. That's my speculation. I can't say I know the answer, because it was designed back in the late 90s, and obviously we've extended it since then. I did not work on it back in the late 90s. So it's speculation, but that's what I think is probably the answer. Any more questions? All right, well, I hope that was really interesting. Thank you for watching. We have a new version coming out next week, so if this made you interested in testing some of this out, and you try the version that we have right now, I think the version that we have in about 4 days' time is going to be a lot more something that I would prefer you to look at a lot more than the current version. But as I said, there's a free version to download and stuff. So if this is interesting to you, you can do that and try it out. Thank you.